Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all again in this particular space. And in this particular video we're going to be able to determine electron number in an orbital given the specific atomic number. And this is going to be quite interesting, but at the same time really tricky, I will put it that way. And looking at this particular question, it says that how many electrons in the sd orbitals are present in an element with an atomic number of 26. And of course, if you go to the periodic table, you should see what element has the atomic number to be 26. And once you have that checked out, you're like, some periodic tables do actually show the electronic configuration of that specific element if you're really curious to check that out. But if you want to go through the long way of getting through this particular answer with a worthwhile experience of getting it through, how are you going to do it looking at this particular question? So before we dive into this, please don't forget to hit the like and share and subscribe. By the way, others can actually get a chance to check out these videos, and also subscribing is free. So looking at this particular question, we need to come up with a plan, because everything is part of a plan. So when we go into this particular question here, we see so many interesting things that actually comes into play and calls to mind. And the plan here first is, first we're asked to determine how many electrons, are in the sd orbital, which means that our end result is to determine the number of electrons in the 3D, what did I say, SD? Sorry, 3D orbitals. And then you will need the following. You will need the element's atomic number, and in here we have the atomic number of the elements to be given. And so it means that we need to go from the atomic number all the way to the number of electrons in the 3D. When you say 3D, just know that we are dealing with, in this case, quantum numbers. And dealing with quantum numbers, you need to take into consideration the energies, and also the shape, and also the orientations, and also finally the spin. So all these four quantum numbers, you need to consider those in order for you to apply atomic number to the number of electrons in a specific orbital. And what do I mean by orbital? The orbital is categorized under the angular momentum, which is represented as L. So that actually is going to be crucial for you to be able to understand what is the maximum number of electrons in that specific orbital in that particular element. So looking at this, our plan here is to first be able to determine the total number of electrons coming from the atomic number, and this will be followed by looking at the energy chart, or considering energy in terms of arriving at that particular distribution of electrons, either in the same orientations, focusing on the same shape, or we look at just single orbitals, like for example S, and so on. So once you have this taken care of, our next thing here, for we to get to our final number of electrons, is to be aware of specific exceptions. And so the exceptions will be really crucial in order for we to be able to keep those in at the back of our minds in order for we to actually successfully arrive at our specific final answer to this question. So solution means that we need to be able to actually come up and follow this particular plan in order for we to arrive at our answer. So take note here that based on the question, we have the atomic number to be given, and the atomic number is equal to 26, which in this case here is equal to the number of protons, and is also equal to the number of electrons. Therefore, since we have the number of electrons to be equal to the number of protons in a neutral atom, this actually implies that in this case here, indeed, the total number of electrons that we are going to be dealing with here is going to be 26. So we're going to be playing with 26 electrons in our energy chart. So on our energy chart here, we need to show various quantum numbers in, or I would say the first three quantum numbers, we got to show those, and then we're going to consider the final quantum number, which is the spin. So looking at the energy, we are going to look at, our energy graph, or I'll put it that way, an energy sketch that will show the different energy levels, and also what are the different orbitals that are present in each energy levels, and then the various orientations that are in the energy levels. So first one is, of course, 1s energy level here, and then the next one is 2s, and then this is going to be followed by 3 orientations of our 2p orbital, and then next one is going to be our 3s, and we're going to move up to 3 orientations of our 3p orbital, and then there's a tricky one right here. Instead of let's go with 3D, we have 5 orientations in our 3D, but take note here, the exception is this: between 3p and 3d is the 4s orbital. So this is one thing to keep in mind here. And you're asking, why is this the case here? This is because that particular energy level is way more diffused, and as a result of that, compared to the 3D orbital, which is more spread out, compared to the 4s orbital, the 4s orbital is actually considered to be a lower energy orbital compared to the 3D. Therefore, in this particular case here, we're going to be focusing on the 4s orbital, which comes after the 3p, and then after the 4s orbital, we're going to fill the 3d. Now, there are some exceptions as well to filling out the 4s compared to the 3d, depending on the spin of the electrons and how stable the energies are when you consider those. So we're not going to dive into this on this particular video, but on our next video, we're going to dive into some of those exceptions. But this is just a first exception to this particular rule involving energies relative to our specific principal quantum number and looking at our specific orbitals. So in this particular case here, we're going to fill up our electrons, and take note, we need a total number of electrons to be 26, so we need to keep track of that. So in this case, we're going to fill this with 2 electrons, and then this as well, 2 electrons. But then since we have 3 orientations, or 3 in the same sub level, then it means that they all have to have 1 electron first, and then we pair them with the opposite spin in order for this system to be stable. And then the next one is we're going to pair this up, and then we do the same thing we did in the SP to the 3p. We add 1 electron to each sub oriented orbital to then becoming a paired system for this to be stable. And then our 4s will be filled first, and then we go to our 3d. So counting, we know that we're going to have 2 here, plus 2 gives us 4, plus 6 gives us 10, plus 2 gives us 12, plus 6 gives us 18, plus 2 gives us 20, and then finally 26 minus, in this case we have 20, we have 6 electrons left, and the 6 electrons, they go into the 3D. And how do you go about this? We're going to do the same thing. We're going to add 1 electron, the same spin on each of the orientations energies, 1, 2, 3, 4, 5, and then we pair it up 6. And so we're able to actually determine our specific number of electrons that are present in our 3D, which in this case here is actually, in our 3D, we have 6 electrons that are present in our 3D. And so Take note here, of course, the exception here, our 4s orbital comes before the 3d. That is really important to keep in mind. So that's about it for this particular video involving considering how to determine the number of electrons in a specific quantum number system given the atomic number of an element. And this is just one case scenario which involves specifically looking at a type of transition metal, which is kind of a tricky one, but it's also fun to be able to approach that. Otherwise, if you cannot actually figure out that it is 4s, 2 as the orbital that comes first, a great way to actually check is using the periodic table. The periodic table tool is set up in a way that you can actually follow this really easily. So in our periodic table, we have this arrangement, and then we actually go all the way to this, and then we go and we finally, we just give a little sketch also. That should be helpful. And so in here we have our period of group 1 all the way to group 18, and in here we have 3 specific periods, and in here we have period 1, this period 2, this period 3, and in here we have period 4 all the way this way. But hey, take note, in between this group 2 and group 13 is the D region, which is transition metals. So the transition metals, they are around here. So in here we're going to have group 3, and we're going to have group, in this case, since we have 10, this is going to be 13, no, 12, sorry, this will be 12, and then it's not going to be 10, no, it's not going to be 10. So you have 3 and you have 12, and then in this case here we're going to go 5, and then this is 6 and 7. So in this case here, when you're filling out electrons, we know that of course we have 1, 2, we have 3, 4, we have 5, 6, 7, 8, 9, 10, and then next one here is 11, 12, 13, 14, 15, 16, 17, 18. Now here we have 19, we have 20. So this right here, group 1 and group 2, they are considered to be the s orbitals, and so the energy level here is 4s. And now once you go in here to the one that we just filled out here, this is actually considered to be the 3, because we're in period 3, and we are considering this particular, always consider this to be the p orbitals, which is our p. So therefore in here we have our 4s that has to be filled up first before entering our 3d state. So our 3d state, we're going to have 6 electrons, so which means that 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 electrons that will be then added to that particular region. So that it shows that you need to fill the 4s first before you get to the 3d, which is our transition metals that represents our d orbital. And our f orbital, which we don't really focus on for now, is actually positioned right here, starting from this particular region and ends right here. So all these are inserted starting from the 4f, and this is our 5f orbital here, right there. So wow, the more elements we discover, maybe we can have our 6f and our 7f's, or maybe we can find a new specific orbital after f. You never know. So that is it in here for how to use the periodic table to also follow through on how to actually determine what particular energy level needs to be filled up first before moving up to a different energy level. So that's about it for this particular video. I hope you found this really informative. Please hit a comment down below. Let me hear your thoughts about this. If you have any suggestions or better ways to approach these questions, you can also jump into the comment section and let me know your thoughts. All the same, thanks for following me through this. Truly appreciate it. Hit the like, share, and subscribe, because of course subscribing is free and others can actually get a chance to check out these videos. And see you on the next one. Stay smart as always and believe in yourselves.